GIS Fundamentals, Section 8, Attribute Data and Tables. Spatial data in a GIS are often split into two components: the coordinate information that describes object geometry, and the attribute information that describes the non-spatial properties of objects. Attribute information in a GIS are typically entered, analyzed, and reported using a database management system, or DBMS, a specialized computer program for organizing and manipulating data. The DBMS stores the properties of geographic objects and the relationships among the objects. A DBMS incorporates software tools for managing tabular data, including those for efficient data storage, retrieval, indexing, and reporting. Note that the terms DBMS and database are sometimes used interchangeably. In most cases, this is incorrect, and in all cases, imprecise. A DBMS is a computer program that allows you to work with data. A database is an organized collection of data, often created or manipulated with the help of a DBMS. While spreadsheets may be used for simple collections of data, database management systems are better for most applications that process large amounts of data. Database management systems provide other advantages. They provide data independence, a valuable characteristic when working with large datasets. Data independence allows us to make changes in the database structure in ways that are transparent to any use or program. This means restructuring the database does not require a user or programmer to modify their procedures. Before data independence became widespread, organizations frequently spent considerable time and money rewriting applications and retraining users with each change of the data structure. Data independence avoids this. A database management system may also provide for multiple user views. Different users may require different information from the database, or the same information delivered in different formats or arrangements. A database management system also allows centralized control and maintenance of important data. One standard copy of the data may be maintained and updated on a regular known basis. Database components and characteristics. The basic components of a traditional database are data items or attributes, the indivisible named units of data. Attributes may be simple, for example, one word or number, or they may be compound, for example, an address data item that consists of a house number, a street name, a city, and a zip code. Items have a type and a domain that restrict the values they may take. Types define essential characteristics of an item. Common types include real numbers, integer numbers, both of various lengths, hexadecimal numbers, text fields, hyperlinks, and binary large objects, or blobs. Domains define the acceptable values an item may take. For example, integers may be restricted to be larger than 10, or larger than 0, but smaller than 10. A collection of related data items that are treated as a unit represents an entity. In a GIS, the database entities are typically roads, counties, lakes, or other types of geographic features. A specific entity, such as a specific county, is an instance of that entity. Related data items are often organized as a row or line in a table called a record. A file may then contain a collection of records, and a group of files may define the database. In the relational database model, the record may be called a row or n-tuple, and the records are typically organized into a relational table. The concept of an entity, when referred to in a database, may be slightly different than an entity in a GIS data model. This difference stems from two different groups, geographers and computer scientists, using a word for different but related concepts. An entity in a geographic data model is often used for the real-world item or phenomenon we are trying to represent with a cartographic object. In contrast, computer scientists and database managers often define an entity as the principal data objects about which information will be collected. In database management system literature, the entity is the data object that denotes a physical thing, and not the thing itself. A DBMS typically supports complex structures, primarily to provide data security, to maintain stability, and to allow multiple users or programs to access the same data simultaneously. A DBMS may be designed to manage multi-user access. Some DBMS manage shared files and data and enforce a predetermined precedence in simultaneously accessed files. The DBMS may act as an intermediary between the files and the application programs or user. The DBMS may prevent errors due to simultaneous access. The DBMS is sometimes referred to as a database server, and the application programs as clients. The server provides or serves up the data to the client applications. The separation of data and functions into multiple levels is often referred to as a multi-tiered architecture. Data are primarily stored at the lowest tier. The system or programs that access the first tier at the bottom of a multi-tier system are often called a transaction manager. This transaction manager typically takes requests from higher tiers and searches the relevant portions of the database to identify the requested data or perform the requested operation. The next tier in the multi-tier architecture is often referred to as an application server. An application server is software that passes requests from higher level tiers to the transaction manager. It converts input from above into a set of instructions the transaction manager below can understand. The application server may check to see if the agent has a profile, and so handle requests in a certain way. The uppermost tier of multi-tier architecture is typically a user interface. This tier may be a display by a single purpose or topic-specific program such as a GIS, or a web-based interface with the primary purpose of gathering requests from the user and presenting information back to the user based on those requests. Multi-tiered architectures are adopted primarily to insulate the user interface from processing and data at lower tiers, and to allow access to a more diverse range of data through the lowest tiers. The parts are easier to change when they are isolated, and new, different resources may be more easily integrated. The integration of a new database technology is often easier with multi-tiered architectures. Multi-user access adds substantial overhead and complexity to processing. Physical, logical, and conceptual structures. A database may be viewed as having conceptual, logical, and physical structures. These structures define the entities and their relationships and specify how the data files or tables are related to one another. The conceptual structure is often represented in a schema. A schema succinctly describes the database structure in standard shorthand notations, usually via entity relationship diagrams, also known as ER diagrams. A schema is a compact graphical representation of the conceptual model, the entities, and the relationships among them. The actual connections within the computer files may be achieved in many ways. One common method uses file pointers to connect records in one file with those in other files. Relational databases. Relational databases have grown to become the most common database design since their introduction in 1968. The relational model is more flexible than most other designs. The table structure does not restrict processing or queries, and the organization is simple to understand, learn, and implement relative to other database designs. It can accommodate a wide range of data types and is not necessary to know in advance the kind of queries, sorting, and searching that will be performed on the database. The tables in a relational database design are also called relations. The rows are called records or tuples. As noted earlier, columns contain attributes or items that describe entities. Tables are related through keys, one or more columns that meet certain requirements, and may be used to index rows. Keys are often columns that uniquely identify every row in a table. Keys are the key to the utility and flexibility of relational databases. The general definition of relational databases defines a relational algebra. This relational algebra takes relations, or tables, as input and returns relations as output. The algebra combines or splits tables, either by rows or columns, to generate subset or expanded tables. The relational algebra may also be used to specify constraints, requirements, and security on a database. Given their importance, there are some restrictions on keys. For example, null values are typically not allowed to be part of a key. There may be many potential keys, or columns that uniquely identify each row, but typically one is chosen for use, called a primary key. Primary operators. The relational algebra supports 8 primary operators: restrict, project, union, intersection, difference, product, which is all combinations of a given set of variables recorded in a database, join, which is combine tables based on matching attribute values, and divide, which facilitate queries based on condition. Relational algebra supports 8 primary operators: restrict, project, union, intersection, difference, product, join, and divide. Restrict and project operations select based on rows and columns respectively to provide reduced tables. Restrict operations can be compound and complex and involve more than one attribute. Restrict operations most often return a reduced set of rows for a table as an output. Project operations return entire columns for a table, in effect subsetting the table vertically. Product operations combine all rows in one table with rows in another table to output a larger table. The divide operation is often the most confusing of the 8 original relational operators. The relational divide is analogous to the mathematical divide in that there is a target, the dividend, that is divided by another table, the divisor. However, the confusion comes in that this is done relative or per a third table. Divide operations are generally used in queries that would use the word all in a natural language description of the request. For example, get states with all 3 major ethnic groups. The remaining 4 primary relational operators, as defined by EF Cod, typically return records based on membership in 2 or more tables. These operators are union, intersection, difference, and join. There are limitations to the application of the union, intersect, and difference operations. The tables used in these 3 relational operations must be of the same kind. That means they must have the same set of variables or items before they can be used in these 3 operations. A union operation combines tables to return records found in either or both tables. The tables are stacked to return a new table with members of both, but it does not show duplicate records for those entries that appear in both tables. The intersection operation returns records that occur in both input tables and omits records found in only one of the 2 input tables. The difference operation returns those records that are in the first but not the second table. The order of table input in a union or intersection operation does not change output. However, with the difference operator, order usually matters. A join operation combines two tables through values found in keys. Hybrid database designs in GIS. Data in a GIS are often stored using hybrid designs. Hybrid designs store coordinate data using specialized database structures and attribute data in a relational database. Thousands to millions of coordinate pairs or cells are typically required to represent the location and shape of objects in a GIS. Even with modern computers, the retrieval of coordinate data stored in a relational database design is often too slow. Therefore, the coordinate data are frequently stored using structures designed for a rapid retrieval. This involves grouping coordinates for cartographic objects. For example, storing ordered lists of coordinate pairs to define lines, and indexing or grouping lines to identify polygons. Pointers are used to link related lines or polygons, and unique identifiers link the geographic features, points, lines, or polygons to corresponding attribute data. Topological relationships may be explicitly encoded to improve analysis or to increase access speed. Addresses to the previous and next data are explicitly stored in an indexing table, and pointers are used to connect coordinate strings. Hybrid data designs typically store attribute data in a DBMS. These data are linked to the geographic data through unique identifiers or labels that are an attribute in the DBMS. Data may be stored in a manner that facilitates the use of more than one brand of DBMS and allows easy transport of data from one DBMS to another. Selection based on attributes. The restrict operator. Table queries. Queries are among the most common operations in a DBMS. A query may be viewed as the selection of a subset of records based on the values of specified attributes. Queries may be simple, using one variable, or they may be compound, using conditions on more than one variable, or using multiple conditions on one variable. Many GIS softwares provide a query builder, a graphical user interface, or GUI, that helps in applying selection operations. Most GUIs include a list of available fields, operations, and a sample or complete display of values for selected fields. The Boolean operations, and, or, and not, may be applied in combination to select records that meet multiple criteria. And combinations typically decrease the number of records in a selected set. Or combinations typically increase or add to a selected set in compound queries. The not is the negation operation and may be interpreted as meaning select those records that do not meet the condition. Relational databases may support a structured query language known as SQL. SQL is a non-procedural query language in that the specification of queries does not depend on the structure of the data. SQL provides the capability to both define and manipulate data. Joining or relating tables. Relational databases are so powerful in part because we can structure out data in ways that reduce duplication, are easier to maintain, and are flexible. Much of this flexibility is because we can join tables. A join, also known as a relate, uses columns in one table to match rows based on columns in other tables. Joins are based on joint items or join fields. In their simplest form, a single column in one table is matched to a column in another table, and a new table created by combining rows for matched values. Primary keys and joins. There are several kinds of keys, but the most important is the primary key. An item, or sometimes multiple items, that uniquely identifies each row in a table. We often create and generate these unique numbers to keep track of things. We typically are very careful about how we assign and when we alter the values of primary keys, in part because of their importance in joins. We must ensure that we don't duplicate key values in a data table, and we have to be careful to not reassign values to the primary key through calculations or other modifications. Many of the errors in databases result from corruption of a primary key. An inner join, or an output row, is created only from rows that match on the join items. An outer join saves the information for non-matching rows, placing blank or null values for the items for rows that don't have a match in the target table. There are both left and right outer joins, depending on whether the source or target non-matches are in the source or target tables. There is also a natural join, in which equally named columns aren't copied, or cross joins, in which all rows in the source table are combined with all rows of the target table. Most joins should involve a one-to-one or one-to-many relationship between the source and the target join items. This is why we usually use a primary key in our source table as the column for a join, or we use an item that could serve as a primary key. This avoids a many-to-one relationship between source and target columns, which often results in problems. A one-to-one relationship means just that. There may be one and only one instance in a join item of a source table that matches one and only one instance of a join item in a target table. Tables may also be unambiguously joined if there is a one-to-many relationship between the source join item and the target join item. We often run into problems when we attempt joins with items that have a many-to-one or many-to-many relationship. These are often considered ill-matching keys in that results from a join can be indeterminate. You can't predict the results in advance, or they may change due to spurious factors, such as pseudo-random effects of row ordering. Foreign keys. A foreign key is an item in a child table that may be used to correctly link the rows in another parent table. Foreign key values unambiguously identify rows in the parent table. We often use a primary key in one table to serve as a foreign key for another table. When multiple columns are used as a key, it is called a concatenated key. Concatenated keys are typically formed by 2 columns, and rarely more than 3 columns. Multi-table joins. We may also join many tables to a single table, often using different target items for each join. Normal forms in relational databases. Keys and functional dependencies. We may place relational databases in normal forms to avoid problems. Data are structured in sequentially higher normal forms to improve correctness, consistency, simplicity, non-redundancy, and stability. There are several levels in the hierarchy of normal forms, but the first 3 levels, known as the first through third normal forms, are most common. Data are usually structured sequentially. That is, first all tables are converted to the first normal forms, then converted to the second and then third normal forms as needed. Prior to describing normal forms, we must introduce some terminology and properties of relational tables. A superkey is one or more attributes that may be used to uniquely identify every record or row for a table. A subset of attributes of a superkey may also be a superkey and is called a candidate key. The primary key for indexing a table is chosen from the set of candidate keys. There may be many potential primary keys for a given table. However, it is usual to use only one primary key per table. Functional dependency is another important concept. Attributes are functionally dependent if at a given point in time, each value of the dependent attribute is determined by a value of another attribute. Functional dependencies are transitive. So, if A is greater than B and B is greater than C, then A is greater than C. The first and second normal forms. Normal forms typically result in tables with repeat groupings. A table is in the first normal form when there are no repeat columns. A table is in second normal form if it is in the first normal form and every non-key attribute is functionally dependent only on the primary key or on transitive functional dependencies of the primary key. Functional dependency means that knowing the value for one attribute of a record automatically specifies the value for the functionally dependent attribute. The non-key attributes may be directly dependent on the primary key through some functional dependency, or they may be dependent through a transitive dependency. Some of these disadvantages can be removed by converting the first normal form table to a group of second normal form tables. To create second normal form tables, we make every non-key attribute fully dependent on a primary key in the new tables. Note that the first normal form table will often be split into two or more tables when converting to a second normal form, and each new table will have its own key. Second normal form eliminates some of the redundancies associated with the first normal form. The third normal form. The second normal form still contains problems, although they are small compared to a table in the first normal form. They can still suffer from transitive functional dependencies. If a transitive functional dependency exists in a table, then there is a chain of dependencies. A table is in the third normal form if and only if, for every functional dependency, such as A is greater than B, A is a superkey, or B is a member of a candidate key. This requirement means we must identify transitive functional dependencies and remove them, typically by splitting the table that contains them. A general goal in defining a relational database structure is to have the fewest tables possible that contain the important relationships and to have all tables in at least the third normal form. Databases may be organized around usage or denormalized for most common processes. GIS Fundamentals, Section 8, Attribute Data and Tables, Section Summary. Selections or queries are among the most common analysis conducted on attribute data. Queries mark a subset of records in a table, often as a precursor to subsequent analysis. Queries may use and, or, and not operations, among others, alone or in combination. Relational tables are often placed in normal forms to improve correctness and consistency, to remove redundancy, and to ease updates. Normal forms seek to break large tables into small tables that contain simple functional dependencies. This significantly improves the maintenance and integrity of the database. Normal forms may cause some cost and speed of access, although this is a diminishing problem as a computer hardware improves.